Okay, so this is the last physics colloquium of the fall quarter, and we're really lucky to have our own Lauren Tompkins, who is an assistant professor in the physics department. Lauren did her PhD at UC Berkeley, and she was a postdoctoral fellow at the University of Chicago. And we've been lucky to have her on the faculty here at Stanford, and where she's been working on making discoveries with the biggest machine ever built, as far as I think that's correct, the biggest machine ever built on Earth. And she's played a role both in helping to build pieces of the machine and also in doing exciting physics with it. So welcome to Lauren, and please go ahead. If anyone wants to ask questions in the chat while we're going, please feel free to ask questions in the chat or to raise your hand, and I'll try to pay attention to those questions so that Lauren can focus. I'll interrupt you if needed, Lauren. Please go ahead.
All right, thanks. Thanks, Risa. So today I'm going to be speaking about perspectives on the LHC, where we've been, where we're going, and that'll kind of lead us into the direction of new frontiers in the search for dark matter. And I think I'm going to start off with the really big picture, which, as Risa said, as an experimental particle physicist, or at least as experimental high energy particle physicist, we like really big things, big pictures, big machines, big budgets, big collaborations. So let's start from like the 30,000 view and then go from there. So as I said, I'm an experimental particle physicist, and what that means is I'm fundamentally interested in the question, what are we made of? So you can ask that question to a lot of different people, and oops, I played this trick with a few of my friends. So I have Jessica Feldman, she's a professor here in biology, and I asked her as a biologist, what is your answer to this question? And she said cells, molecules, and atoms, and then she clarified that she really only said atoms because she knew she was talking to a physicist. Then you can ask the same question of a chemist. So I asked my brother, who's a chemistry background. He says carbon, hydrogen, nitrogen, oxygen, and a smattering of other elements. Next step down this chain would be going to a physicist. So I asked Monica, who we're all friends with, what is your answer to this question? And of course, she gives a very physicist-y answer and saying, well, it depends on how fundamental of an answer you want. But as an atomic physicist, my first answer is atoms. And if you ask me as a particle physicist, what I'll say is, we're made out of electrons, protons, and neutrons. And then I'll probably clarify to you that protons and neutrons are made up of quarks and gluons. And so that's where this game ends. As far as we know, quarks, gluons, electrons have no substructure. You can't subdivide and find another doll. But once you're at this point, what you find yourself trying to do is understand what makes a quark, or an electron, and what are the forces and fundamental symmetries that dictate how, for example, a quark and a gluon will interact. I will note, I also asked this question of a psychology professor here at Stanford, Aaliyah Crum. She said, we are made out of, I believe it was thoughts, feelings, and expectations. I had to sit with that for a minute because it's a kind of deep answer. But anyways, moving on. So what is our picture of the fundamental particles and how they interact? This is the standard model. It is divided up, you see, into 4 different components. So we have the quarks and the leptons, which make up fermions, to make up matter. And then we have the force carriers over on this side. And then we have the Higgs boson, and I'll get to what all of these are. So normal matter, you, me, the universe, is made up of, at least in the matter component of it, and the visible matter component of it, is made up of this first column here, which is the first generation of matter. So we have the up and down quarks and the electrons, and then the electron neutrino. And then for the fermions, there are 3 generations. So we have 3 columns here, and in each case, the particle has the same quantum numbers as the column before. The only difference is its mass, which we will find is essentially a quantum number for these particles. If we look at the forces, there is the photon, which mediates the very familiar electricity and electromagnetic force. We have the gluon, which mediates the strong force. So that binds quarks into protons and neutrons, and it binds protons and neutrons together to make nuclei. And then we have the W and Z bosons, which may be less familiar, but they're responsible, for example, for weak nuclear decay. And at the center of this all is the Higgs boson, And it is the particle that gives mass to all other particles in this picture. So we'll get much more into the Higgs boson in a minute. But I wanted to share with you sort of the more technical picture of the standard model. So this, on the left, I have the Lagrangian, the standard model. And what you can see is that it's massive. It has many terms. These terms represent interactions. And what you see is that, if you consider each one of these terms as an interaction that can be probed and explored, you find that we have a very rich and complex theory with many facets to explore. But there are some issues here. So first, it seems to be fine-tuned such that many big numbers cancel each other. There's a so-called hierarchy problem where the Higgs mass is tied to the scale of gravity. It can't explain dark matter, which will become important at the end of this talk. It can't explain the dominance of matter over antimatter in the universe. And it can't explain a lot of other things, such as why do we have 3 generations of particles? Where do neutrino masses come from? What about gravity and dark energy? So while we have this very beautiful and predictive theory, we also know that there are outstanding problems that we are searching for explanations for. Okay, so I want to get back to the Higgs boson. So the Higgs boson is actually just the manifestation, the physical manifestation of the Higgs field. And the Higgs field is a fundamental field which exists everywhere, everywhere at all the time in the universe. So this is contrary to sort of any other field that you think of where you need something to generate the field. The difference in the Higgs field is that it's there all the time. And the reason that it is there all the time is that its minimum is at a non-zero field value. So this schematic here shows a Higgs potential. And what you can see is at the center, which is the 0 field value, you are at a high energy state, and here particles have no mass. So gravity, photon, the weak boson, neutrinos, electrons, soft quarks, all of them would have no mass, which is indicated here by the lines for these particles just traveling in a straight line. But the way our universe actually sits is that the minimum of this potential is actually at a non-zero field value, which means you have a Higgs field existing everywhere all the time. And so particles which don't interact with this field, gravity and the photon, remain massless. But particles that do interact with this field, so the weak bosons, the neutrinos, the electrons, the top quarks, they acquire a mass, and the strength of the size of their mass is proportional to their coupling to this field. And the picture's a little bit more complicated for the weak bosons, but just bear with me in the general, this sort of general analogy here that how strongly a particle interacts with the Higgs field generates its mass. And so this potential tells us a lot about the mechanism for mass generation in the universe and about something that is present in the universe at all time. And so we better learn about it. So you can characterize this potential in a few terms. So there's the first term, which is related to the Higgs boson mass. We have a term that's related to the Higgs self-coupling. And then we have a term that's related to the Higgs fermion coupling, so how the non-gauge bosons acquire mass. And so a lot of what particle physics is trying to do, and particularly what the LHC is trying to do, is to understand, is to measure essentially the parameters of this potential and understand, is it in fact the right potential at all? Okay, so I want to give you another analogy for the Higgs mechanism, which if this this field description didn't work so well from you, and you're gonna have to bear with me for a minute because this analogy feels a little wrong in COVID time, but it's the classic way that the Higgs boson is explained. So we're gonna go through it, and we're going to imagine we are not all in shelter in place. So you're at a conference, and this is a conference dinner, and there is food and drinks on one side of the room, and all the people, the attendees of the conference, they are going to represent for us the Higgs field. So how is something going to gain mass by interacting with the Higgs field? So what we're going to do is we're going to see how a person who's going to be our particle in this sort of analogy gains a mass by traveling from one end of the room to the other, so to try to get to the food. So if someone really famous walks in, like maybe Einstein, he's going to be mobbed, and everybody's going to want to talk to him, and so he's going to be continually interacting with the members of the crowd, and so that's going to take him a long time to get to the other side of the room, which would be him having a large mass. We could have, a new graduate student who knows may be the next Einstein, but at this point, nobody knows who they are. They're going to be able to traverse this room relatively quickly. And so then you could have them seeing as having a small mass. So that's just another way to kind of wrap your head around a sort of real world picture of what a real world analogy for what the Higgs mass would be. And if you don't like that one either, one more analogy, which I think is useful to think of, is a particle's electric charge is proportional to how strongly they interact with electromagnetic fields. You can think of mass essentially as a Higgs charge. So a particle's mass is how strongly it interacts with the Higgs field. And that's the one I personally like the best. All right, so how are we going to find this Higgs field and how are we going to measure this potential? Well, in order to do this, we need to produce Higgs bosons and study Higgs bosons. And so in order to do this, we need to use a very large microscope. And why do I call it a microscope? Well, as you learn in sort of first year quantum mechanics, all particles have an associated wavelength, and that wavelength is inversely proportional to their momentum. So that means that you can probe high energies of high momenta with small wavelengths and vice versa. Or you can probe small wavelengths with high momenta. So then once we have our very high momenta particles, which can allow us to probe very small length scales, we can essentially use the relativistic energy momentum equation, E equals mc squared, or its full version, E squared equals m squared c to the fourth plus e squared c squared, in order to produce particles with heavy masses from particles with low masses. And this can give us particles which are important on the scales. It reproduces conditions, for example, where the average energy density of an interaction was very similar to what the energy of an interaction was in the early parts of the universe. So with the Large Hadron Collider, when we're colliding protons at a center mass energy of 14 TeV, as I'll explain in a minute, we're probing time of about 10 to the minus 10 seconds after the Big Bang. All right, so what is the Large Hadron Collider? So the Large Hadron Collider is a proton-proton collider that is situated at the border between France and Switzerland. There are 4 large experiments which exist at this machine. I personally am a member of the ATLAS Detector, and that's what I'll be focusing on, or the ATLAS experiment, and I'll be focusing on that here. So the LHC has collided protons at a range of center of mass energies, anywhere from 900 GeV to 13 TeV. To just give you a sense of reference, the rest mass energy of a proton is 1 GeV, so 13 TeV is 13,000 times the rest mass energy of a proton. We've also, I'll not talk about it here, but we've collided lead ions and also protons with lead ions in order to actually probe the real conditions that were similar to shortly after the Big Bang. How do we do this? So this is achieved with about close to 10,000 magnets, which are used for both bending, focusing, and correcting of these beams. They all operate at 1.9 Kelvin, so colder than outer space, and they have a maximum strength of about 8 Tesla. So that bends the beams, and to accelerate them, we have 8 RF sections, which operate at 400 megahertz, and these accelerate at a peak strength of about 5.5 megavolts per meter. So if we were to situate, center the LHC on Stanford campus, just to give you a sense of scale, it stretches pretty much past 101 to 280. So it's a pretty darn big machine. All right, so I wanted to go over, so there's something quite peculiar about, we were in a rather unique situation with the LHC in that we could basically guarantee a discovery. So there's not many experiments that you can do where you can say, I am guaranteed to discover something. But we really sold the LHC on the fact that we had a sure bet here. And I felt like it's instructive to step through a little bit of this sure bet. So there were 3 papers that came out in the mid-60s, actually 1964 to be exact, from Angler and Brout, from Goralnik, Hagen, and Kibble, and then from Peter Higgs, who the name, who the Higgs mechanism's name take, but they all basically established this phenomenon that if you had a potential with a local minimum and a non-zero field value, then you could generate masses of gauge bosons and gauge theories. So this was established. And at the same time, there were people who were trying to assign a theory to essentially the proliferation of different particles and interactions that they had been observing in accelerators at that time, primarily accelerators at that point at that time. And so I'll focus here on Weinberg. There's other people who contributed this, but for example, Weinberg put together a model of both leptons and for hadrons that we would now recognize as the electroweak interactions. And this electroweak interactions had massive gauge bosons. And so we knew from work done by Peter Higgs and others that there needed to be this sort of Higgs mechanism in order to generate mass. And so there was, I think, a period of time of roughly like 10 years where people were trying to figure out really what are all the implications of this. And in going back and trying to find the specific paper which gave the sort of no-lose theorem for the LHC, I found even our own Andre Linde had done some work. I guess this must have been right at the tail end of when he was a graduate student, or maybe just after he graduated, where he was put a minimum bound on the Higgs mass by working through the implications of this theory. And he also pointed out that the different parameters of the potential needed specific values in order to generate this spontaneous symmetry breaking. So I thought that was kind of nice. But the no-lose theorem here came when you looked at the upper bound of what was possible within the theory of electroweak interactions. So there was this paper in '77 by Benjamin Lee, Chris Quigg, and unfortunately I don't know who H is, but Thacker. And they basically showed that if you look particularly at the scattering of vector bosons, so the scattering of W bosons, as a function of the center of mass of that scattering, in order to keep the theory physical, either you had to have a light scalar boson here of a mass well below 1 TeV, or this interaction will start to exhibit something that goes with the strongly coupled theory. So we would end up having resonances, so new other particles that were showing up in the scattering of vector bosons. So this is actually really important. It means that if you build a machine that can access vector boson scattering at 1 TeV, then you know that you will either see a new scalar boson, so that would be our Higgs boson, well below that, or you would see some new phenomenon that comes in at 1 TeV. And so this is why we were like so sure that when we built the LHC that we were going to be able to see the Higgs boson, which then also makes building any other accelerator a little bit more challenging because we don't necessarily have this no-lose theorem. But in any case, I think it's instructive to remind ourselves of that. Okay, so how do you make and detect a Higgs boson? So there are 4 different ways to make a Higgs boson. Well, there's a few more than that, but these are 4 primary ways of the LHC that we probe. So the most common is so-called gluon-gluon fusion. So here, the 2 gluons, one from each proton, through the heavy quark loop, so usually a top quark, form a Higgs boson. The second most prevalent and one which I will also talk about, and particularly it relates to that vector boson scattering that I just mentioned, is where the quarks from the incoming protons each radiate a vector boson, and those vector bosons fuse to form a Higgs. So this essentially was the light scalar that was being talked about by the previous paper I discussed. And there are 2 other methods, one of which is when a vector boson radiates a Higgs, and another is when you produce that Higgs in association with a heavy quark, so typically a top quark. So that's how you produce the Higgs boson. So how do you, it decays, so a Higgs boson decays nearly immediately. So we're in a pretty lucky situation where the Higgs decays to a lot of different types of particles, so that means there's a lot there to measure. And so the most prominent decay is to B quarks. About 57% of Higgs decays to B quarks. Then there's varying other rates. The next most common is W bosons and gluons. And okay, so gluon is massless. This happens through another one of these top quark loops, taus, charms. And then you get down to Z bosons and photons. And while these are actually 2 of the least common Higgs decays, they're actually the ones that we use to discover the Higgs, and that is because they are the ones that have the sort of least background. Okay, so it's not quite the whole picture. So you can identify that you have 2 photons, you have 2 Z bosons. And then in order to decide that, or to figure out whether or not they came from a Higgs, you create the invariant mass of these 2 objects, so measuring their 4 vectors. And then if they have an invariant mass that's out of the Higgs, then you can start to say whether or not you have a new particle. Okay, so how do we measure those 4 vectors? So this is the ATLAS experiment. It is about 50 meters long and 25 meters tall. Here are people for scale. And since we just like went through Thanksgiving, my favorite analogy for a particle detector is a turducken. So a turducken, because it's many layered and each layer is different and unique and special. So the innermost layer is tracking detectors. So these measure the trajectory of charged particles, and they are immersed in a 2 Tesla magnetic field. Then outside of that, we have calorimeters. These are devices which are able to measure the total energy of particles that interact electromagnetically and also through strong force. And then outside, the detectors that give the ATLAS detector really its gigantic size are muon detectors. And so we have an air core toroid here, and detectors which indicate the presence that a charged particle is passed, and the only type of charged particle which passes all the way through those layers of the detector is a muon. All right, so we have like an artist's rendition of how particles are accelerated in the LHC. So we take protons and accelerate them from rest through a number of staged accelerators. And we're not just accelerating individual protons. There's about 3,000 bunches of protons in the LHC at any given time, and each one of those bunches has about 10 to 11 protons per bunch. So it's really quite a bit of protons. Here we're going through a stylized version of the LHC tunnel, and now we're traveling along with one of the protons. You here are seeing some rendition of 3 quarks in 3 different colors. Quarks coming, it's the charge of the strong force. And so they're going to meet in the center of the ATLAS detector here. And now this is real data. So what you're seeing is real data from a collision. All of the white lines are the reconstructed trajectory of charged particles. And then what you have here in the 2 green areas is energy deposited in the electromagnetic calorimeter, which are consistent with the presence of 2 photons. Sorry, my computer has kind of fallen over here. See if I can go forward. So anyways, this is what a Higgs boson, an individual event looks like. Okay, good, we're not stuck. So that's an individual event, but we can't say whether or not any individual event is a Higgs boson. So I wanted to show you what the data was from the Run 1 Higgs Discovery. Here, these are 2 histograms. On the left, we have the invariant mass of 2 photons. On the right, we have an invariant mass of 4 leptons, which come from the decay of 2 Z bosons. And what you're going to see is the x-axis is going, the y-axis is going to have the number of events which occupy that invariant mass bin. And this is going to be increasing as we have a function of time. So here we're seeing the photon channel start, and the background estimation is this blue line. And what we have on the bottom is the difference between the blue line and the data points. And what we're looking for is the emergence of a signal. So here what we're seeing for the 2 photons is that the data are very consistent with the Higgs mass here at this point of 126 GeV. And over on the other side with the Z bosons, the background prediction is this red histogram, and some also from the purple histogram. And then you see a big excess here at also around 125 GeV, and that is consistent with the Higgs signal. So that's how we discovered the Higgs. But that was happened right around in 2012 and 2013. It was confirmed, and then we went into shutdown. And after that, we had what we can call the honeymoon phase, or the getting to know you phase, where we started to collect a statistically significant sample of Higgs bosons, and this lasted from 2015 to 2018. This plot shows all the total amount of data that was recorded during this period, so-called Run 2 period. There's 2 things to note here. One is that in green was the amount of data that the LHC delivered, and in blue was the amount of data that the ATLAS detector was on and operating in a good state for. And so you can see we have very good efficiency. The detector had very good efficiency with respect to the total amount of delivered luminosity. And then I wanted to put this into some, this is a unit of total integrated luminosity, which means something to you if you are an experimental experimental accelerator-based particle physicist, but if you're not, probably doesn't mean much. So we could look at this in terms of the number of Higgs bosons, and the number of Higgs bosons that correspond to the good for physics data is about 7 million. Now, that's 7 million based off of all those different decay modes, and many of them are not actually usable for us, but that does give you a sense of scale for how much data was taken. All right, so what did we do in run 2 with these Higgs measurements? So first I'll note that run 2 ended in 2018, but we are still putting out measurements now that have just finished analyzing this data. So this is a lot of this work is really actually hot off the presses from this summer or this fall. So as I said, we're trying to figure out this potential term. So we've been able to measure the Higgs boson mass. This is combined measurements in both the 4 leptons, so the ZZ channel, and the photon channel. And you can see we have a variety of different measurements. The combined average measurement for the ATLAS experiment is here. And you can see we have a Higgs mass of 124.97 GeV with an uncertainty of just 24 MeV. Oh, sorry. And then you can look here at the particle masses in GeV. So this is a plot of the particle mass versus the coupling to the standard model. And what we want is coupling to the Higgs boson. And what we want to see is that there is a linear trend here. So that the Higgs boson couples to particles as a function of their mass. And we see here pretty good agreement with that line. The measurements of the tau lepton, the fermion, so the tau lepton and the B quark have larger error bars, so about 20% error bars. This is the top quark measurement, and the measurement with the Z and W bosons are significantly more precise. And then we can kind of look at this in more dimensions. So we are looking at the ratio of cross sections in the different production modes. So vector boson fusion, then the associated production and the TTH production. And we can compare those to the standard model expectation of 1. So here we've normalized everything. So you just have to see how much something has deviated from 1. And what you can see now is that to the extent, to the precision that we have so far, and you notice like this is 50%, 1.1 here is 50% off the standard model. We have agreement with the standard model. So we've done more than just measure those couplings. We've also started to measure differential distributions. So this is a measurement of the Higgs boson PT, so essentially how much energy is put into the Higgs system. And this can be modified. You can observe new physics in this distribution if there's something else that's coming into this Higgs-ZZ interaction. So here the plot shows the data in black and then various theoretical predictions in the various colored points. And this plot here shows the difference between the data and theory. And while there does seem to be some small amounts of shape difference, it's all consistent within the errors. Similarly, you can look for contact interaction. So this is another, just any form of modification of this interaction between the Higgs and the 2 Z bosons in the function of different bins, which represent different Higgs boson production topologies. And okay, so we haven't seen any difference between the standard model and the data, but again, the uncertainties are large. And in many cases, to really make progress for discoveries in new physics, we need something on the order of 1% or a few percent precision. Okay, so the Higgs is not all that we've done. So as I mentioned, the big set of the standard module Lagrangian means that there is an enormous amount of items to look at. And this plot represents over 14 orders of magnitude, the measurements that we've been able to do. Definitely not going to go through this, but this plot is just to impress you with the number of measurements of various supersymmetric signatures that we've done. And we've looked at a wide range of exotics. This is, again, each one of these lines represents at least one measurement of an exotic scenario, ranging from extra dimensions to heavy quarks to leptoquarks. So this is mostly just to show you that we have a very broad physics program that is happening at the LHC, and we have nearly 1,000 publications from ATLAS so far to date. So it's part of why we need 3,000 people to do this. We have about 3,000 people, so you can figure out about everyone's on at least 1/3 of these publications. So what's next? So we're here, we're in the middle of this long shutdown too. And sometime in 2022, and we don't know yet when because of COVID, the LHC is going to start up again, and this will be run 3. And so in run 3, we're only going to get 2 times the statistics of run 2. And when you're looking at rough estimates of sensitivity, you tend to do this as the square root of n. So you increase your sensitivity roughly as the square root of n. So this means a 40% increase in sensitivity. So if I'm being honest, like if all you were going to do is repeat what you did in run 2, which, you know, you might think you should do because you're not increasing the center of mass energy anymore. So, you know, what else is there to do? You're not going to find things that are that exciting. But what I hope to convince you is that there are at least 3 ways in which we can do better. And what I'm going to do is show ways in which you know, some of my group has shown we can do better with stuff, taking examples from run 2. So one way you can do this is to improve the hardware. So the LHC produces more data than we can keep. So it's about 50 terabytes per second. This is the total Library of Congress's total collection every second. And so experiments use fast hardware and software to peek at the data and decide what to keep. So this allows us to reduce the 40 megahertz event rate to about 1 kilohertz of storage rate. And the challenge is that you have to do this efficiently with up to 60 simultaneous collisions, and you're looking for things for like a Higgs, which is 9 orders of magnitude less than the total collision rate. All right, so what can we do? So we can improve, one of the things we can do is improve the trigger decision by including more hardware. So I want to talk to you about a project that my group was heavily invested in, which demonstrated that you could use tracking information, so the trajectory of charged particles in the trigger, and give you a lot more information for making your decisions. So this is not done currently because tracking information is the most dense and most costly, but we developed a system where we use fast algorithms and hardware in order to reconstruct these charged particles. So what we did was we divided the detector into slices, and then we fed in all of the hits from the detector into these chips here, which are custom associated memories, which essentially have bingo cards. And they have bingo cards, which say where you get a bingo if you have the data that you receive matches the trajectory of a charged particle. And we can do 1 billion simultaneous comparisons, and from this fit 1 track for every 5 picoseconds. And this is a really large system. We had 9 separate components, thousands of PCBs, thousands of FPGAs. And we were able to do a test run of this in run 2. So here this shows just some of the hardware that my group produced and installed and designed. And up here in the right, this shows we were able to install this for 1 slice of the detector. It shows tracks reconstructed by our system in a run in 2018. In the bottom, we have plots of the data taken by the system in black compared to the full simulation, which is in red, where you see good agreement. And so what this can be quite useful for is, for example, large impact parameter tracks, which are present in for particles that have some finite lifetime, missing energy. We can look at B triggers and taus, and also something called particle flow, which allows us to improve the resolution of jets. And we demonstrated this in a detector slice. As I mentioned, we demonstrated this in the detector slice in 2018. So this was discontinued. So we were initially planning to install this in run 3, but the LHC was initially planning to increase the intensity of collisions from 60 to 80 average simultaneous collisions in run 3, but we decided to stick at 60, and then there was also limited experiment resources. So this project was not continued. However, both ATLAS and CMS are exploring similar systems for use in the high luminosity LHC. So this is definitely not the end for this hardware-based tracking, and I'm really proud of what my group demonstrated in terms of feasibility here. So the next thing we can do is analyze smarter. So one of those, I'm going to use Higgs to B quarks as an example here. So this is a very abundant decay mode, but it's also very challenging. The set is 57%, and the problem is there's a lot of things in collisions that look like 2 B quarks, so 2 jets. This just shows you some Feynman diagrams that can produce 2 jets, and by contrast, there's relatively few things that can produce 2 Z bosons or 2 protons. And so that's why we're able to discover with those cases. So one of the ways, if you can't essentially discriminate based off of the Higgs decay products themselves, you can target production channels with something else in the final state. So typically this is done by using the vector boson fusion. So you can find a Z or W boson here and look for an associated Higgs. And what my group did was look at vector boson fusion, the vector boson fusion case. And so just to give you an example of how you can make big improvements, in 2016, we took the 2016 data, which was a small data set, and we used a machine learning classifier called a boosted decision tree in order to separate our events into things that looked like just normal jet production, so QCD production, and those that looked like vector boson fusion production. And then we were able to divide up this data sample into the most signal-like and the least signal-like, and then do a fit to both the background sample and the signal in order to extract what amount of Higgs boson we could find. This is done in a log likelihood fit. And what you see here is that we found this plot here were the results where you have the ratio of the observed value to the standard model. So 1 would be something that was exactly the same as the standard model. And this was the measurement that we did. And what you can see is that we measured something that was 4 times the standard model, but had an uncertainty of 3. So that's like, statistically consistent with the standard model. And we knew we could do a lot better than this. So in taking the full data, which we had from run 2, which was 4 times the amount of data, we used a new machine learning classifier called an adversarial neural network. And in this case, what we were able to do was we were able to tell the network, okay, I want you to be able to distinguish between signal and background. But what I want you to do is I want to make it such that you don't learn anything about the invariant mass distribution of B quarks. So I want your output, your decision of whether it's a signal or background, to be independent of that. And what that allowed us to do was use the same background shape in all of our regions that we're using to fit the Higgs boson. And because this then basically increased the statistical power of the fit significantly, we were able to greatly reduce the uncertainty on the Higgs boson signal. And so I should have mentioned, this was Christian Nunez did a lot of work in the implementation of this adversarial neural network, and he's an undergrad here. And what we were able to do was improve our results. So if you remember, the uncertainty that I had previously was around 3. We had measured a central value 4 with an uncertainty of 3. We are now measuring a central value of around 0.95 with an uncertainty of 0.38. And so we improved this by 7 times. And if you remember what I said about an increase in statistics, this usually goes as a square root of n. So the naive expectation would have just been a factor of 2. So this is just all to say that in run 3, you could have a lot more data available to look at than what, you have a lot more in your data than what you've already looked at. And I just want to note this result was just featured today in an ATLAS physics briefing. So if you want a short synopsis of it, you can go to our website. So after run 3, we have the High Luminosity LHC, which is going to improve the statistics by a factor of 10. And the highlights here, part of the way that we increase the statistics so much is by having now 200 simultaneous proton-proton collisions. Here the point is that we're going to be able to improve the uncertainty on the couplings lot. So this is all the Higgs decays to the various types of particles. The green is what you got with run 3, and the blue is what you will have with the High Luminosity LHC. And you can, and this is the relative uncertainty. You can see beat uncertainties of about 20% very easily. You're also able to measure the Higgs self-coupling, which is an important parameter in that overall Higgs potential. My group is working here. We have a few people working here on charged particle reconstruction algorithms for the High Luminosity LHC. And going beyond that, there's talk of building a larger 100 TeV collider. So here would be at CERN, and there's a variety of other options for building a Higgs factory. I'm not going to go into detail of this, but I just wanted to impress upon you how long of a program this is. It's essentially 50 years from now, having to realize the full potential of these measurements. All right, so rush through that because I'm running a little bit low on time. So I told you there are 3 ways that you could make, run 3 more interesting. And the third is to look in new places. So essentially you look at places where you don't know. And to do this, we first need to talk about dark matter. So for dark matter, there's abundance of astrophysical evidence for this. And what we know is that of the energy density of the universe, 23% of it is in dark matter, as opposed to the 4.6% of it in the sort of normal matter that comprises the standard model. So if you look at what are the possibilities for what dark matter could be, the first thing you notice is that the standard model does not have a dark matter candidate. And the non-standard model possibilities are nearly endless. So this gives you a broad range of so-called dark sectors, where the mass range goes from zeta electron volts all the way up to 30 solar masses with black holes. So although it's not strictly necessary, and most models have the dark sector connected to the standard model through a portal interaction. So essentially we could have a rich dark sector, which then can talk to the standard model through one or more mediators. These dark sectors can be rich, just like the standard model. They can have multiple particles, they can have multiple forces, and they're appealing because they can solve other problems. So there's the strong CP problem, which is solved by the QCD axion, which many people here at Stanford are searching for. There's baryogenesis, neutrino masses, the hierarchy problem. So these different types of portal interactions allow us to do that. So I'm going to take one assumption with dark matter, and I want to make the assumption that dark matter was in thermal equilibrium with the standard model in the early universe. And this is going to allow me to narrow that gigantic range. And I think most people would agree that that's a pretty mild assumption, essentially. So once you do this, this means that the relic abundance of dark matter is fixed by the rate of this coupling of the dark matter to the standard model and the mass of the standard model. So it's called freeze out. And so one example of this are weakly interacting massive particles, so WIMPs. And WIMPs have been the most popular dark matter candidate to date, because if you simply use this formula, this thermal equilibrium formula, and you put in for an interaction strength that of the same scale as electroweak interactions, then you automatically get a particle out that's at around a mass of 100 GeV. And this naturally comes out in, for example, supersymmetry. So there's been a really big program looking for WIMP-based dark matter. There's a lot of people here doing that. So CDMS and LZ, and that's a pretty well covered sector. And what we're finding is that they're doing really great at excluding large regions of this parameter space, which has started to get people to think elsewhere. And so it's important to remember that WIMPs are just one thermal dark matter candidate. And in fact, this simple requirement of thermal equilibrium gives a dark matter mass range from order around MeV to about 10 TeV. And so this is all, these are all masses that are accessible at colliders. And I encourage you to check out Natalia Toro's talk, or colloquium she gave 2 years ago on exactly this thermal dark matter. So I think just given time, I'm actually going to skip the ATLAS, dark matter ATLAS part, because we are looking for dark matter at ATLAS, but I just don't think it's quite as exciting as dark matter that happens in other dark sector experiments. So I want to start talking about probing dark sectors with electron beams. So here, this is work that I've recently joined some Slack colleagues, so Tim Nelson, Philip Schuster, and Natalia Toro on. And so if you limit yourself to light thermal dark matter, so the mass of the dark matter less than about 10 GeV, this naturally implies small couplings and low total energy, which means that the LHC is not the right tool to go after that. So a better tool is to use high intensity electron beams on fixed targets to search for what we would call dark BREM as a baseline. So that is shown here, where you can have essentially 2 cases of this. So you have an electron beam. It interacts with the nucleus in your fixed target, and then it radiates a dark photon. And that dark photon can either decay to dark matter if its mass is greater than 2 times the dark matter mass, or it can decay back into electrons because you have this dark matter interaction. So there are more complex scenarios like this. So for example, with Jess Fry, who's an undergraduate here, we're looking for strongly interacting dark matter at the heavy photon search, experiment, which looks for the decays of dark photons to electron pairs. And here it's essentially looking for a dark QCD. But what I want to focus in the last few minutes here is on LDMX. So LDMX stands for Light Dark Matter Search, and it's a proposed new experiment looking for missing momentum at SLAC's end station A. So that's SLAC's end station A is a very historic end station where proton structure of the atom was found. Of the proton was found, and it's a beamline that will be off the LCLS beamline. So in phase 1, there's going to be a 4 GeV electron beam, and what we'll have is that beam incident on a target in where the target is in the center of a tracking detector, and then when the electron radiates a dark photon, the dark matter will travel through the detector, and what we'll measure is the recoil electron here. We've got a calorimeter to measure the electron. So this is an experiment that has, these institutions are involved, and sort of to give you a sense of size, it's much smaller than the ATLAS experiments, just a few people high. So the really cool thing about LDMX is that with phase 1 of LDMX, we'll be able to cover a large fraction of the thermal dark matter model. So how do we do this? So we will essentially be measuring two things. We'll be measuring the recoil energy of the electron. So this plot down here shows that recoil energy for different dark matter mass scenarios compared to the background, which is the single inclusive electron background. And then if there happens to be a discovery of dark matter, we can use the transverse momentum of the electron to distinguish between different types of different masses of dark matter. This bottom plot shows the sensitivity of LDMX as a function of the dark matter mass. These black lines here are the predictions from relic density dark matter estimates. So basically something to be consistent with a thermal dark matter, and it happens to be elastic and inelastic scalar, then it has to lie on this line, or fermion on this line, etc. So what you can see is that the phase 1 of LDMX actually excludes, or is sensitive to a large range of these thermal dark matter candidates. So my group is working on the LDMX trigger. So the trigger is here on missing energy in the electromagnetic calorimeter. And in order to accurately know how much missing energy we expect, we need to know the number of electrons that are in our detector. So we're working on the part of the detector that determines how many electrons are there. We're using fast simulators to do electron counting in 2 microseconds. And then we're also working on the global trigger, which does combines all the information in order to reduce the full event rate from 37 megahertz down to 5 kilohertz. LDMX has received R&D funding that goes through 2022, and then it is presumed that we will start construction in 2023, 2024, and start taking data in 2025. The first phase is just going to be 2 years of data taking, and then we will upgrade the detector for higher energy running and higher intensity running in 2027 and beyond. All right, so I'm going to end there. I believe the LHC has made impressive progress in understanding the Higgs boson, but I just want to emphasize that realizing its full potential is a long haul, and it requires a high luminosity LHC, and it requires effort of just like a real community-wide effort to get that done. To make progress with REN 3, we're really going to have to get creative, both in the analysis that we do and the signatures that we explore. And I'm pretty excited in the sort of near term for opportunities for dark matter discovery at accelerators close to home. So thank you very much. This is a photo of my group from a recent party that we had. I'll put it there so you can see the question Zoom window.
All right. Thanks so much, Lauren. Lovely talk. Please feel free to raise your hand for if you have questions. I'm going to call on Giorgio first.
Okay, thanks. Okay, let's see whether I'm muted. Yes, okay. Thanks, Lauren, for the nice talk. I have a sort of a exotic question, and going back to triggers of LHC and in general experiments where you have those tremendous improvement of signal to noise, essentially. And that is, as anybody, so the reason you can do that, of course, is that, you know, your events are very specific in terms of topology, as we call it, maybe improperly, energy distributions and all sorts of things, right? So you actually, essentially, you know, you just use all those parameters. There is another totally unrelated area where you do this fantastic signal to noise ratio, and that is what we're becoming all familiar with, is you know, amplification of DNA, essentially PCR sort of amplification, whatever it's called. Has anybody ever checked how the two compare with each other? You know, in other words, whether you know, who's better, and you know, so you know, in other words, how much information there is and how much constraints there are in the PCR case, and how they sort this thing compared to what is done at colliders. It's just curiosity.
Yeah, so I don't know. Maybe someone has done that. Yeah, sorry, I don't have a good answer. I'm trying to think if there's any like number I have in my head that's relevant, but I don't think I do. Sorry.
Yeah, because I don't know how.
It'd be cool to calculate that, but I don't know.
I don't know how to define the complexity of your events, of course. And you know, if you go down to minimum bias, that things get, you know, there is certain things you peel off from the very beginning, and other things where you use more this. Anyway, I just thought this was actually kind of a, you know, it may be interesting to think about that way. And yeah, anyway, that's.
Okay, more questions. Shaman? Go.
Yeah, sure. I mean, I'll ask a super naive question, which is, I mean, can you comment on the likelihood that just from Higgs branching ratios, where, you know, we'd see new physics that people sort of thought about in the old days, anytime in the next, you know, decade, just from indirect signatures of the lack of unitarity in branching ratios to what we know?
Yeah, so Higgs branching ratios are really not the best way to do this. They're the most straightforward to kind of understand in some sense, but they really aren't the best way to do that, partly because it's just really hard to get good measurements of them. But I think the differential distributions that I've talked about, which give you quite a bit of sensitivity to, you know, anomalous couplings, that's a really good place to look. And doing some of these ratios of various couplings is where you're going to see the difference. So I think, I'm not sure if, let me remind myself if the slides for the FCC gives us, I can't find it. Here we go. Yeah, so I mean, these are the major targets for the FCC, which would be the, you know, the sort of ultimate in, you know, what we're thinking about in terms of colliders. And you can get down to sub 1% on the couplings for things like TT, HBB, and such, but you really need to get to FCC to do that. You can't really do it with high luminosity LHC. You need to get any deviations is going to be on the 1% level, and you just don't get there until you get to an FCC. So I guess I amend my answer to say, at the high luminosity LHC, you're not really getting that, but at some place like an FCC, higher energy collider, you can actually get the precision that you need.
Thank you.
Okay, Eva?
So I'm curious about your machine learning results. So could you say a little bit more about how the adversarial neural network works? Is one of them trying to fool the other one by generating training data for it or something, or how does that work?
Yeah, so it's a little, so adversarial neural networks are usually set up like where they're used for like image creation and stuff like that, is where you have an image, you reduce it down to like the classifier output, and then you have another classifier that learns to reconstruct the image from that. This is a little different. We're actually combining two different types of classifiers. So what we have is the sort of our input classifier is a binary classifier. So it just says, is the signal or not, while we're trying to have it distinguished. And then our adversary is actually categorical. So what it's trying to learn is what is that MBV value, and it's trying to reconstruct that from the classifier output. And so, yeah, and then what you do is you put this all in a combined loss function, such that the better that the adversary does on learning the MBV value, so the invariant mass of the B quarks, then that penalizes the overall loss function. So yeah, and this works well, for example, so this works well when you're already constructed to be, okay, so let's put it this way. You still get a good classifier out of this when your classifier itself is already not super strongly correlated with the variable. So like if I had really strong correlations, you just essentially that extra loss function would just overwhelm the my binary classifier. But what we found in this case was like really we just needed a little bit more, like we needed a little bit more decorrelation, and this adversarial component really does it. I mean, I should say it's just kind of cool and nice connection. Michael Kagan at SLAC, who's one of the SLAC Canopy Fellows, he's one of the people who first came up with this idea.
Thank you. Sorry, just to follow up, is this the sort of method that could, or any of the machine learning methods that could in principle, a machine learning procedure find a pattern that theorists didn't think of to test, something like that, or is that just really hard to get error bars for that are convincing?
So people are doing things like anomaly detection. So essentially you train on some known data and you look for an anomaly. The hard part is getting a good training sample for that. So either your Monte Carlos you have to trust well enough, or and in most cases, for example, like this sort of concept of a model and fully model independent search has been around for a long time, but just given the sort of diversity of possible processes in the LHC, sorry, my daughter just came home and she didn't freak out. Sorry, that makes it very difficult to do these things. So usually it's much better to have a specific hypothesis, but that being said, there are a lot of people who are looking specifically at that. There's been an interesting thing called, which is another anomaly detection work, which is called learning without labels. So it's kind of similar where the labels essentially, or the categories are learned from the data itself. And I think that's a pretty interesting thing. And there's been some comparisons between that and what you would get by doing like Monte Carlo based labeling. That can give you some good insight.
Peter.
Hey, thanks for the nice talk. Actually, I just wanted to follow up on Shamat's question because I realized this is something I should remember, but shamefully I can't. Even independent of Higgs measurement, Higgs branch ratios, things like that. Are there good examples of any kind of measurements you can make at the high luminosity LHC where you could get, let's say 5 sigma discovery? Even assuming we don't get any hints at the remaining regular LHC runs. I mean, there are examples of new physics where we could get all the way to a discovery at high luminosity, even given the current situation, let's say, at the LHC.
So I've mostly been paying attention to Higgs. So just full disclosure, I've mostly been paying attention to Higgs stuff, and a lot of that the most spectacular cases are in di-Higgs production. And so, yeah, di-Higgs production, you could see resonant new phenomenon or modification. So beyond just standard model di-Higgs production, you only barely see at the high luminosity LHC. But if there is any sort of new physics, that could very easily come up at high luminosity LHC, not at LHC. I have seen, there's some SUSY scenarios where mass splittings are really, really big. And they're predominantly sort of these like electrobeam SUSY areas where I'm pretty sure the high luminosity LHC buys you a fair amount there, but I'm not expert enough in that to give you like a definitive answer.
Got it. Thanks.
Do we have one more question? Okay, well, it's perfect timing. If not, let's thank Lauren again. And to since this is our last colloquium of the quarter, let me just say, have a wonderful break, and hope everyone gets a little bit of downtime over the holidays, and we'll come back to this weird virtual world in January.
Bye. Thank you.
Thanks, everyone.
Thanks, Lauren.
Thanks, Lauren.